Okay, so now we are going to talk about aldehydes and ketones. It is in Unit 3, and we see the syllabus first. It's about aldehydes and ketones. So what we are expected to learn from this chapter is uh, structures and structures of carbonyl groups, preparation of aldehydes and ketones from acid chlorides, 1,3-dithiones, nitriles. Then we need to know what is the mechanism of the nucleophilic addition to carbonyl groups, with a particular emphasis on the benzoin, aldol, Perkin, Cannizzaro, Novenagel condensation. Then reactions of these compounds with ammonia and its derivatives. Reduction of aldehydes and ketones with lithium aluminum hydride, sodium borohydride, aluminum isopropoxide, Voigt-Fishner and Clemmensen reduction, oxidation and aldehydes of ketones with oxidizing agents such as K2Cr27, KMnO4, and also with the mild oxidizing agents which are toluenes, salins, Benedict solutions. Oxidation of ketones, haloform reactions, Baeyer-Villiger oxidation, the structure of carbonyl groups, preparation of aldehydes and ketones from acid chlorides, 1,3-dithiones and nitriles. So this is going to be the first thing that we have to start talking about. And okay, so we go down and try to see the carbonyl structure, right? So as we can see, we have made a carbon and oxygen bond over here. This is a single bond, but then since it is a double bond, we know, so it has got to have a 1pi bond, which is like this, right? So we have this 2pz orbital, which is in this direction. We have a pi bond, and then we have a sp2p bonding taking place, right? Because this one is of the sp2, right? I mean, this is a p orbital, this is sp2, 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 right? And this is a p orbital, and the same thing for oxygen, right? Oxygen has a 2-lane pair of electrons, so it is in a way 1, 2, and then you have say like this HH, right? So oxygen 1, 2, 3, 4, a 2 lone pair and 2 sigma bonds, so it has sp3 hybridization. Actually, what it then does is, since it is a lone pair, so we can also kind of say it has a 2p. I mean, you minus it becomes 1, and then you make it and so then you start saying that sp2 of this and p orbital forming a pi bond. So we see over here, this is a pi bond, this is sigma sigma, and this sigma pi pi, right? How do we prepare it? Preparation of aldehydes and ketones from acid chlorides. So we are trying to prepare it by acid chlorides because these are good starting materials. Cl can easily go outside of the system, and we can replace this with our desired atom or a group. We shall also be learning to prepare it by 1,3-dithiene and nitriles, right? So let's start. So it is a preparation of aldehydes and ketones from acid chlorides. So a well-known reaction is the Rosenband reduction. Basically, it is just a reduction in presence of metal, right? But we also put in some poison, sulfur, barium sulfate. So what is happening? It is a reduction of this thing to this one. Why we are calling it reduction? Because we have a CCl. Instead of CCl, we are now going to have a CH. So it is a reduction, right? So what we need is a palladium, barium sulfate, and sulfur, and the solvent is going to be the boiling xylene, right? Say we have PHCOCl, and then we have PHCHO formation taking place. We can also prepare it with the help of a dialkyl cadmium compounds. Why? Because these are something which has a kind of a the carbon of this alkyl group attached to the cadmium has a sort of a delta minus charge with it, and what is then happening is, say you have RCOCl, so this R minus kind of a delta minus kind of a thing coming into the system and removing Cl, getting displaced. So ultimately we have a ketone formation taking place over here, right? We can also make it with the help of the lithium organocuprides. Here it was dialkyl cadmium. This is organometallic compound, right? RMX. This is a metal ion, and here again we have a R, and then metal ion, right? This. So we are going to talk about this thing, right? So how does it happen? So we have a lithium organocuprides, right? And this method we are utilizing it to prepare ketones only. So lithium dialkyl cuprates react readily with acid chlorides to form a ketone in an excellent yield. So you have a acid chloride, RCOCl. We know that it can be removed very easily. If we can bring in some R minus kind of a character into the system, so it gets attached to carbon double bond and Cl minus gets displaced. So we are again using a less reactive organometallic compound, say in the form of a lithium organocuprate. We are using solvent as a dry ether. Temperature is 196 Kelvin, which is lesser than 273 Kelvin, right? So it is a minus degree centigrade. So we have a formation of a ketone taking place, and organo copper compound, lithium chloride, right? Now, how do we prepare from the 1,3-dithiones? So in order to know about it, we first need to know what are 1,3-dithiones, right? So we have a starting material something like this. I redraw it. So it is a 1, 2, 3. So 1, 2, 3. So we have a 3 carbon, and then I draw it like this, SH, SH, okay? And if I get it converted into this form, right? So this becomes 1,3-dithione. 1,3-dithione. Why? Say I started make it as a 1, then it becomes 2, 3, and 1, 3 di 1, 3 1 1 and 3 di for the sulfur, and since it is a heterocyclic compound, so we name it like thia, and ane for the 6-membered heterocyclic compounds, right? So that is how we name it as a 1,3-dithione. Now, what are the advantages of using 1,3-dithione? Well, see this structure, right? We have something like this, okay? So if we want to know whether this H would like to get removed in the form of a proton, H plus. If it happens that way, then what we are left with is like carbon ion over here and H plus over here. So this becomes minus thing, right? So we are happy to see minus charge because we have a carbon minus charge, right? As I've already been saying for a very, very long time, that in organic chemistry we are always kind of looking for an opportunity to get carbon in the form of a carbon ion, because most of the organic chemistry we have a R attached to a particular atom which is on the right side of the carbon in the periodic table. So that means they are more electronegative. So automatically it is something like this, R is a, but we are then looking for an opportunity to make it like this, and then we can allow it to get closer to the R plus, and we then have a RR formation. So that is how the number of carbon increases, number of atoms of carbon increases, right? So that is the advantage of the 1,3-dithione. The advantage is we are getting a carbon in the form of carbon having a minus charge, right? So like here, what was happening? We were bringing R minus with the help of a organometallic compound, right? So this was an organometallic compound. The same principle we are trying to do over here. In fact, as we build up this chapter, we shall be using We shall be seeing aldol condensation kind of a thing, and the principle employed over there will be carbon having a minus charge onto it, right? So we have this thing. So this is 1,3-diethyene, and we are okay. So how do we prepare 1,3-diethyene also? Because as I mentioned, we have like things like this, SH, and we are using HCHO. So HCHO is like this, right? I'm using an acid, H plus. So what does acid does? It goes to this oxygen, so it becomes carbon. On oxygen we have a plus charge. So ultimately it becomes something like how do we okay, so it then becomes like this, OH, and I'm left with a plus charge on the carbon, right? And sulfur is a good nucleophile. It has a 2 lone pair of electron onto it, so it can attack onto this one. So then I have something like this. This is SH, this becomes SH, now it becomes plus, and this is like this, and then you have a OH over here, right? Now with time, what will happen? This H plus will come onto this one, this OH, right? So then I have a thing like this becomes SH, this becomes again S, and you have a carbon, this, and OH2 plus. Now when I see OH2 plus, this is a OH2 plus, I feel happy. This is a OH2 plus, this thing, right over here, it is a OH2 plus. I feel happy because I know that when I have a system like this, let me redraw this thing. Maybe I explain you on this one. So I have like this SH. So I had this one. Okay. So it comes onto this one. Before that, we have this one, H plus acidic system. So it comes onto this one, right? This is plus. So it becomes like this, and then I have this thing, right? This comes over here, and then this particular pi bond, since oxygen is a plus charge, so it kind of pulls pi bond onto this one, and it becomes like this. Okay, we still have and this is plus, right? So we still have a acidic medium, so this goes like this. Either I put H plus over here, or maybe I can bring this H plus over here. Either way, maybe I do it like this, so it becomes like this. So this becomes OH2 plus. So that way I feel very happy to see OH2 plus, because it is a very good leaving group, right? How does it happen? See, this is also having a lone pair of electrons. So what does that does? It undergoes an SN2 mechanism kind of reaction, backside attack, and ultimately OH2 plus gets removed, and then I have this thing, S, and then it becomes plus since it is a H, and this is a carbon, hydrogen, and this thing, right? So ultimately I can say that it has become a 1,3-diethyene kind of a system, because I have like this. Okay, so I make a 1,3-diethyene system with the help of this particular entity, right? Dithiopropane, 1,3-dithylpropane, and I react with a formaldehyde, right? And that is how I'm getting this thing. And again I say, reiterate that the advantage of this particular system is that this H is acidic. Acidic means if I put a base over here, then this is going to become like this. Now you will say that this shall be a very kind of a unstable system. right? But the thing is that you have a minus charge, you have a sulfur, and sulfur has vacant d orbitals. Okay, so they have vacant d orbitals. So they can be kind of accommodated in these two sulfurs. So that way this becomes carbon minus charge becomes very uh, stabilized, and also becomes unreactive. It becomes stable, right? So coming back to our thing, uh, and yeah, so we learn how to make 1,3-diethylene, and we are taking advantage. So this is a base. This nitrogen, deuterium, lithium is a base. Why? Because we have an organometallic compound. So this is plus, this is minus, right? So this, if this hydrogen is acidic, it can pull, it can abstract this H plus, and then you have a minus charge generation over here. What is the advantage? Well, you started with this compound, made it you started with 1,3-diethylene, and allowed it to react with the base, and then you have a carbon ion formation taking place. You have a carbon, you have a minus charge over carbon, and you can very easily get it reacted to a Rx, because Rx is having a delta plus and this one is having delta minus, so it goes over here, and so you have a RH. Now you have this thing, right? And then you start reacting with mercuric chloride, methanol, and water. What do? They kind of rehydrolyze the system. Well, as we will see further in this chapter, we shall be having a formation of acetals, right? Uh, hemiacetals, acetals, right? And if in place of oxygen we have a sulfur, so we can then call them thioacetals, right? So these kind of a systems reminds us of that thing. I mean, basically in acetal we will find that we will have a carbon and we will have oxygen on two oxygen attached to this particular system, right? So we will see that thing in future. For now, this is a dithioacetal, which can be easily hydrolyzed with water and in presence of a catalyst, the mercury chloride. So it comes back into this form, and then we have a aldehyde formation again taking place. One can say that we made this thing with the help of an aldehyde. Yes, we made it. We got it formed with the help of an aldehyde. That is correct. But the fact is that we are exploiting it to put more number of R into the system. So we are kind of allowing number of carbons to get increased. Okay, so that is a good thing about it. Also, we can use nitriles. So we have a RCN system. In RCN, we have something like this. So nitrogen is more electronegative. I can write it like this: RC double bond double N minus. Okay. And then I allow it to react with a Grignard reagent kind of a thing, or organometallic. Well, I know this is minus, so it has got to come to this place, right? So when it comes to this place, I have something like this, RCR, where it is coming over here. So RCR, right? And then double bond N, and this is a minus, so obviously MgX of the RMgX is going to get attached to this, and then I hydrolyzed it, right? So hydrolyzed means R. Again, we are going to see in this chapter when we have something like this, and if I hydrolyze it in presence of water or using any acid, so this N shall get converted to oxygen, right? So this will become something like this, and that is what is happening over here. So it is becoming RCOR dash. Okay, so we, with the help of a nitriles also, and also employing any organometallic compound, say like RMgX, RLI, I can get ketone or aldehyde formation taking place, right? Mostly it is ketones. Okay. Okay. So we move a little bit further. Okay. So again, this talks about synthesis of ketones only, and I employ 1,3-dithiene system. I know these hydrogens are acidic. They are going to come out of the system like H plus. We are going to have formation of this. I feel very happy when I see C minus. I keep on saying like this in organic chemistry. Whenever we see C minus, we are very happy because we have a abundance of compounds where we have a R or carbon having a positive charge. So so C minus is going to help us grow synthesis of the generation of new carbon containing compounds, more number of carbon containing compounds, right? So we can put in one R. If we want, we still have a one hydrogen, so we can put another R into the system. We employ a base that abstracts this H plus, right? So it becomes minus, and then this another Rx molecule, and we allow it to get a new compound where we have two R on the one particular carbon. We are increasing the number of carbons, and then we hydrolyze it. As I said earlier, we can hydrolyze it, but the condition should be that we use one particular metal, mercury chloride, which helps us in the form of a catalyst, and we are hydrolyzing it, and methanol is a kind of a solvent into the system. So next we have to talk about the relative reactivities of aldehydes and ketones in nucleophilic addition reactions that I shall be talking in the next lecture.